we now look at the guides to the solution of recommended problems that I have asked you to review. In the first part of this review, we look at internal flow. Now, in the question, chapter 14-2, we are asked to discuss why pipes are circular in cross-section. It is interesting to reflect on this answer because usually liquids are transported in circular pipe because with pipes of circular cross-section, notice the ball face can withstand larger pressure differences between the inside and the outside without undergoing significant distortion. If you notice, air conditioning pipes or ducts are rectangular because pressures inside the ducts are usually slightly above atmospheric pressure. Next, the question 14-9C, we are asked to discuss the effects of roughness on the pressure drop in pipe flow. Remember, in turbulent flow, tubes with rough surfaces has much higher friction than with smooth surfaces. Thus, surface roughness leads to a larger pressure drop in turbulent flow. However, it's very significant to remember in the case of laminar flow, the effect of surface roughness on the friction factor and pressure drop is negligible. I brought this up when we discussed about the roughness on pressure drop. Okay, you notice in the equation for laminar flow in the Moody chart, the friction factor did not depend on the roughness, but only the Reynolds number. Okay, here you have the relationship for laminar flow. F is equal to 64 over Reynolds number. You notice in that equation, and I repeat, there is no term that requires you to know the condition of the pipe. Next, in question 14-26, we look at a rather more extended answer, and this involves a fair bit of calculation. It's not difficult, but tedious. You are given the average flow velocity in a pipe, your pressure drop, the head loss, and the pumping power are to be determined. We need to make assumptions. We are assuming, as usual, that the flow is steady and incompressible. The entrance effects are negligible, and thus the flow is fully developed. The pipe also has no components such as bends, valves, and connectors. It's rather simplistic, but it focuses us on looking at the core requirement for calculations. The piping section involves no work devices as pumps and turbines. In other words, there is no head input or head output. The density and dynamic viscosity is given from tables. And first of all, very important, we need to determine the type of flow. Reynolds number tells us that the flow is clearly laminar. Okay, we plug in all the terms following the formula. It's worth noting that in this case, the dynamic viscosity is required. Since you have less than 2,300. Some people say less than 2,000. Okay, the flow is clearly laminar and the friction is 64 over the Reynolds number. We can then use the Darcy equation to obtain the pressure drop. The friction factor calculated, the length of the pipe given, the diameter given, and rho v squared over 2 given. Pretty straightforward, but rather tedious. Now the head loss, remember, is the pressure drop divided by the density times the gravity, times acceleration due to gravity. So all we need to do is divide the pressure drop by rho g, and we get 19.2 meters. It's good to reflect on this answer. It simply tells us in a visual sort of way, the energy loss, which is the pressure drop, is the same as lifting up the water ahead of 19.2 meters vertically. Finally, the volume flow rate and the pumping power. Volume flow rate is the velocity times the area of the pipe. We get 3.77 times 10 to the power of minus 6. Okay, pretty small flow rate, but remember the unit meter cube per second is a very large unit. The power is simply the pressure drop times the flow rate. I think I've been emphasizing this point in seminar 1 and 2 and 3, and I think you get the hint that this is a pretty important formula. Flow rate in meter cube per second, pressure drop in kilopascals. We convert it to pascals by multiplying by 1,000, and you get quite a small power, 0.71 watts. Okay, so remember, if the flow is laminar, it doesn't mean that the power consumption is low. It just so happens that this flow rate is very small. Therefore, the power input is needed, 0.71, to overcome the frictional losses purely due to viscosities. If the flow were turbulent instead, the pumping power would be much greater because the pipe condition needs to be calculated also. In question 14-75, we are given a cast iron piping in a water distribution system, and it involves a parallel section with identical diameters but different lengths. So please note the diameters are identical, but the lengths are different. You are only given the flow rate through one of the pipes, and you have to determine the flow rate through the other pipe. You have to do a calculation. So remember, when water comes to a junction, it divides into two sections. The very important point that you have to realize is the flow divides, but the pressure drop between the point of division is the pressure drop between these 2 points are the same whether you go through the shorter pipe in this case, or the longer pipe. What in fact happens is, because the longer pipe will give rise to higher friction, the shorter pipe will give rise to less friction. So you will notice that the flow rate will drop in the larger length pipe compared to the shorter length pipe. Anyway, let's get through the calculations. Again, assumptions: steady and incompressible flow, entrance effects are negligible, flow is fully developed, minor losses, that is bends, fittings, valves, elbows, are negligible. We are assuming that the flow is turbulent and the friction factor is independent of the Reynolds number, and this we are going to compute later on. We're going to verify it. The density and the dynamic viscosity from the tables are given, and you are told that this is a cast iron pipe, so the roughness of the pipe is given in terms of meters, okay, 0.26 millimeters or 0.00026 meters. We first find the velocity in the pipe A. We know the volumetric flow rate, Q. We divide by the area, and we get the velocity in the shorter pipe to be 5.69 meters per second. Now, very important point to note when the two pipes are parallel, as I mentioned earlier. When two pipes are parallel in a piping system, the head loss for each pipe must be the same. Head loss in pipe A or in the upper branch must be equal to the head loss in the lower branch. When the minor losses are disregarded, the head loss for fully developed flow in a pipe of length L and diameter is given by the Darcy equation FL over D V squared over 2G. Writing this for both pipes and setting them equal and noting the diameter A is equal to the diameter B and the friction A is equal to the friction B, we can simplify it and we will get a velocity of 3.267 in the lower section, pipe B. Therefore, using the volumetric flow rate calculation, we get the volumetric flow rate as equal to 0.231 cubic meters per second. It's good to reflect on the answer. You notice that in the shorter pipe, less friction, the flow rate is higher. The longer pipe, higher friction, the flow rate is less. Okay, so although the head loss between the 2 points are the same, the flow rate in the upper and the lower branches are significantly different. Now, I leave it as an exercise for you to go over that the proof that fully developed turbulent flow and the friction factor is independent of the Reynolds number. If you recall, the lines in the Moody diagram are all horizontal for fully developed turbulent flow. So go through this calculation. I won't say it's a calculation, it's a proof that you can see that using the Moody chart that the relative roughness, okay, in both pipes are pretty much the same and valid for this question. This ends the tutorial review.